Okay, thank you very much. So we'll. This is my third attempt at introduction of ergodic theory. So today I want to prove this Howe Moore's theorem, which fits nicely with what Manfred was talking about yesterday. But I forgot to give you homework on the first lectures from yesterday, so this is a digression for 5 minutes. Remember we talked about topological dynamical systems and we discussed unique ergodicity. There are several groups of various things. And here is, so the convex compact set of t-invariant measures. Well, unique ergodicity is when this is a singleton, but sometimes it is not. But these measures are all, well, it's always non-empty set. They're all functionals on continuous functions, so you can consider the vector subspace, turns out to be closed subspace, of all those functions from x to, let's say, c, which are continuous. So I should have written just cx. And such that, maybe call it r, such that the inf of integrals f d mu over all invariant measures is equal to the sup f d mu over all invariant measures. So these are, you can think of this as some kind of the upper integral value of f, and this is the lower. So these are just some numbers associated with a continuous function. They can be always defined. This is of course the other way around. So there is a trivial inequality between them, but you can look at those functions for which there is equality. In the case of unique ergodicity is exactly so xt is uniquely ergodic if and only if this v equals c of x, right? So what I'm trying to say is that here is an exercise to prove that all for f in v, the conclusion of unique ergodicity still holds, even though the system is not uniquely ergodic. The average is converge to this common value, I of f, uniformly. Pointwise and uniformly. There is some. Okay.
Alex?
Yeah.
Can you perhaps use a larger script? So
Sorry?
can you increase your
Yeah.
with a larger script? Thank you.
No, but I'll do better with the rest. So you can also look at those functions for which this conclusion holds and call them uniform functions. This is also a closed vector subspace of Cx. And what the other exercise would be, now this second one is challenging, but if xt is minimal, which means that every orbit is dense, then these two spaces, the space for which uniform convergence holds and the space for which all invariant measures agree on the functions is the same space. Just some cute side remarks. Now this is a challenging problem. Okay, now to the actual Howe Moore, to the actual topic of today, theorem. Let me just start off with completely, it looks completely unrelated. First of all, groups enter into the picture. They entered yesterday in Manfred talks. But let G be, well, technical terms would be something like connected, center-free, semi-simple, without compact factors. Let's say this will be R. That's good enough. So this is a prototypical example of a simple Lie group. And suppose that you have an interrepresentation of this on some Hilbert space. So this is a Hilbert space. You should think of L2 of something. And G acts on this by unitary transformations. We say that we have a unitary representation. Is that, the font size?
In the voice also a little bit.
Okay. So then there is...
More bass.
What?
More bass if you can.
Okay. So this is the interrepresentation, which means that this is homomorphism from the group G to this unitary group, but it also, part of the assumption, this is not a discrete thing, this is itself a topological group, so we require that this is continuous. So a continuous interrepresentation is phi is a homomorphism which is continuous in the strong operator topology. Okay, this is the more math, but what it really means is that GM converges to, if a sequence of elements of a group converges to identity, then for every vector in the Hilbert space, phi GM x converges to x in norm. Okay, this is the assumption. You will see that this is really crucial for what I say. Now, once we have such a thing, people look at what's called matrix coefficients. Matrix coefficient of phi is what? Well, given two vectors x, y in H, you consider a function on G given by, your Hilbert spaces should be a complex, kind of a complex. So f x, y of G is the inner product of phi G x, y. And why is it called matrix coefficient? Because if you take some basis to H, think of it finite dimensional for a moment. So you have finite dimensional Hilbert space, which is just C to the n. You take two, you have an orthonormal basis, then your representation can be written by matrices, which are unitary matrices. And if you take the ith and the jth elements for x and y, then what this is precisely the ith j entry of this unitary matrix in the image. Since you don't want to choose basis, and this is infinite dimensional Hilbert space, instead of writing down infinite square things, you just look at all possibilities for various x and y's, and each of them defines you this thing. But this being a group, you fix x, y for a moment, and you look at this as a function of g. Okay, so such a thing is called matrix coefficient. Okay, and here is this theorem. It says that if g is like here, so this is the interrepresentation of, and G is, let's say, simple Lie group. And by this I mean, yeah, something like SLDR. Assume that there are no G-invariant vectors. So no vector of of the Hilbert space is fixed by all elements of G. There's no direction which is fixed. If there are by G invariant vectors, then you look at all of them. This is a closed subspace of the Hilbert space, and you can look at the orthogonal complement. Now, one of the main reasons people look at unitary representations is the fact that they are totally reducible. No. Well, that they, once you have an invariant subspace, the orthogonal complement is also invariant for the unitary representation, and you can just restrict, throw away all the invariant vectors and look at this thing and work there. We'll have an example in a second. So if this is the case, then for every x and y in H, the matrix coefficient is in C0 of G, which means that they go to 0 fxy of G goes to 0 as G goes to infinity. To go to infinity in a group like this means leaving compact sets. So you have a sequence of elements leaving compact sets. Then the matrix coefficients go to 0, or if you look at this, it means that given any two vectors, applying longer and longer elements in the group to one of them, the things become asymptotically orthogonal. Okay, this pi gx goes somewhere, but it tries to be in the hyperspace perpendicular to y. Okay, this is the theorem. We'll apply it if I'm going slow. So I hope maybe I'll apply it now. So an application. The geodesic flow on a finite volume Riemann surface is ergodic. In fact, mixing. Okay, I'm not going to remind you what the basic flow is. I'll just write it down and refer to Manfred's lectures from yesterday and maybe today. So what you look at is you look at the space. So you have your surface. So this is surface of genus at least 2. It has a Riemannian metric of constant negative curvature. You've chosen that. There are many such metrics, but you fix one of them. That gives you an embedding of the fundamental group of the surface in the group of isometries of the universal cover, which is the hyperbolic plane. So this gets embedded in the isometries of the universal cover of this, which is the hyperbolic plane, and also happens to be PSL2R. Well, that's not exactly the isometries, but the orientation preserving ones. This is orientable surface, so no group lands there. And this embedding, so this is going to be my G, and the embedding of gamma in G has finite volume fundamental domain. So you take X to be this G mod gamma with that volume or Haar measure, with G invariant Haar measure, normalized to be 1. That gives you a probability space. On that space, you have a transformation, so you fix time, fix some T0, say positive, and look at the element A which is e to the t0 over 2, e to the minus t0 over 2. Okay. Now, and you look at the transformation of x to x, t sub a maybe, which takes g gamma and maps it to, g translated by a on the right. I'll try to keep this talk consistent with Manfred's talk, but I might sacrifice consistency within my talk. I will do an effort. Now you look at this, and the point, so geometrically what this does is x like that is this unitangent bundle to this surface. So points here determine tangent vectors, and what the transformation does, it takes such a thing as an input. You imagine continuing it as a geodesic. You travel along that distance t0, and the place where you end and the direction in which you end is the result of the transformation applied to this x. And the claim is that this is ergodic. In fact, it is mixing, namely, I'll write it down in a second. The way, so claim that for every AB measurable subsets of X, mu of A intersect T minus NB as n goes to infinity tends to the product of the measures of those sets, which means that it's sort of, they become independent from each other. And the way to conclude it is, so this is called mixing, and mixing is even better than ergodic, because if you happen to have an invariant set, E, you take A to be E and B to be E, you substitute here, being invariant you will have here E, and this would be mu of E, converging, namely equal to mu of E squared. The only solutions to that is mu of E equals 0 or mu equals 1. So being mixing is stronger than being ergodic. And we claim that this conclusion follows from Howe Moore's theorem. How does it follow? Well, what you do is you take unitary representation. I'll erase the theorem. Well, to deduce the claim, take the unitary representation being L2 of x mu, but L2 0. The orthogonal complement, the space of all those functions of which the integral is 0. Okay, this is the orthogonal complement of constant functions. Constant functions form an invariant vectors, because by shifting, constant doesn't change. Ergodicity, and therefore functions with 0 integral, is also invariant subspace. Now, I want to say that I have a unitary representation of G into this unitary group of that Hilbert space. How do you do that? If you have a function in that Hilbert space, phi G of that function is a new function, and its value at x is phi of, okay, well, what is x? X is coset. Now I used G here for element of G. I also need points in x, which x there is G mod gamma. So let me write this. H, so this is a point x. And I want to tell you what the value of this is, and the value of that is going to be phi at gamma hg. So you just translate on the right, you act by g, so not only these elements act on x, all of the group G acts on this. In fact, it acts transitively. Note that the space of invariant functions is now 0 because an invariant function would be constant function, but the constant function whose integral is 0 is 0. Okay. There is a technical detail to check here that this is really unitary representation, namely that it is a homomorphism. I hope it is. If not, then put in -1 somewhere. But there is a slightly delicate issue of continuity, but it is continuous, and this is kind of some fact deduced from Furman theorem, but I don't want to go into this now. Now, by Howe Moore, you will have that if you have a vector little u, which is the characteristic function of A, minus a constant, which is the measure of A, such a function and such a function, they're both in my Hilbert space. These are L2 functions, well, they're bound with 0 integrals. By Howe Moore, since there are no invariant vectors, we have that the inner product of pi a and uv goes to 0 as n goes to infinity. Right? Because powers of this element go to infinity. And if you do the calculation, you will see that the thing on the left is the difference between this and this product. It's just computation of the inner product. Okay, let's prove Howe Moore's theorem. It's a beautiful theorem. So I think historically what happened was people studied examples like this, like geodesic flow and four-cyclic flow, and like Hop, Edmund, Gelfand, many people did, and proved in various ways ergodic properties such that ergodicity, mixing, and further. And then Moore realized that this could be proven using these extra symmetries for Riemann surfaces at least. Not only the geodesic flow acts there, the whole SL2R acts there, or PSL2R, which is basically the same thing. And you should exploit these extra symmetries, and you get stronger results which apply to the broader context of unitary representations. Okay. And then the theorem of Howe Moore passed from ergodicity to mixing. So we're jumping right into mixing. So theorem of Howe Moore goes like this. Suppose not. That's the first crucial step. What does it mean not? So there exist x and y in my Hilbert space, and the sequence going to infinity in G, such that fxy of Gn by absolute value is greater or equal than some epsilon 0, which is itself positive. So there is this, and epsilon 0. Okay? So if there is no mixing, suppose that this is the situation, and this, remember, is a unitary. Okay, so there is step 1 that we want to do. Step 1, reduction to diagonal elements. Now, I want to do things for the case of SLDR. And in this SLDR business, there are several decompositions that are very useful in semi-simple groups in general. So we, Manfred mentioned the Iwasawa decomposition yesterday, but today something not Gram-Schmidt but polar decomposition, also known as KK. Take K to be the SOD, the orthogonal group. Now K be the group of diagonal elements. Now diagonal element like that will have determinant 1 if the sum of the t's is 0. And if d is 2, then you will have t and minus t. But in general, we have this slightly more complicated thing. And here is a fact, and that is that G is KAK. Every element of G can be written as a product of orthogonal, followed by diagonal, followed by another orthogonal. Well, it could be the same orthogonal, but usually not. In fact, and this is known as polar decomposition, or finding axes of ellipses. In statistics, it has some other fancy name. I forgot. Just learned it. Principal factors analysis, something like that. All of that is very useful, but I'm not going to remind you how it goes. I want to say that in A, there is actually a semigroup. For SL2R, it's going to be the ones e to the t, e to the minus t, where t is positive. So for R, the semigroup is just half-life. For general thing, I can look at A plus, which is a subgroup of, sub-semigroup of those, or a cone in here, which is given by the condition that this is equal to 0, and T1 is greater or equal than T2, greater or equal than TD. So you can always arrange this middle thing to be diagonal with decreasing or non-increasing entries, exponents. This is by just permutation, which can be absorbed into K. And to be safe here, let me drop this. Oh, maybe I'll keep it. Anyway, it's true. Let's not worry about that. So we have this, and we can write, therefore, Gn, every element in that sequence, I can write as, it's very important to keep notations right. That is crucial. Kn minus 1. Okay, I want to write it as little kn, an, rn, where kn and rn are kind of rotations, and an's are something like this. In fact, I might want to call kn the inverse of what I put here. So you write it like this. Now, since k is compact, without loss of generality, so we had this, so any passing to a subsequence, I still have the same thing, right? So I'll pass to a subsequence such that Kn converges to some little k in K. Because K is a compact group, I can do that. Okay? Now I can pass to further subsequence so that Rn converges to R in K. Right? I'm not changing the indices. Now, because of continuity, pi Kn of sorry. Let me say that this was U and V. So I had initially U and V vectors in the contrapositive assumption. And now I'm making an assumption that this thing, well, it's not an assumption, call this xn. This is, so if U were a unit vector, now we just rotated it to another unit vector. But because Kn converge to K, this will converge to the vector x, which is pi K of U. Okay, convergence in the norm. Similarly, if I denote by yn this thing, pi Rn applied to V, I will have a convergence to pi R of V. And I claim that if I'm looking now at the matrix coefficients x, y, so now I'm going to apply this to these vectors x, y, but instead of elements gn, I'm going to use those diagonal elements. I claim that this is asymptotically, or going to be greater equal than epsilon 1, which is epsilon 0, which is still positive. So I started from a pair of vectors and some sequence which was not mixing. I get another pair of vectors and another sequence, this time along diagonal subgroup, which is not mixing in slightly weaker form. Why is that? Because if you look at this thing, so I'm looking at matrix coefficients of fixed vectors x and y compared to matrix coefficients which are varying things. But I want to say that this goes to 0. And I want to say that this is like that. Well, you do a little calculation, but first of all, notice that how do you treat such things? It is inner product of pi an x n yn, and you need to compare it to pi an x y. Well, the natural thing to do is introduce a mediator which is mixed. It has xn but y on the other side. So you subtract and add it. Inside here. And by triangle inequality, you see that this is pi an x n here against yn minus y plus, and here I have pi an x n minus x against y. Now, this goes to 0 because y is a fixed vector, xn converges to x, and these are unitary. So by Cauchy-Schwarz inequality, this is less or equal than the product of the norms. Maybe I'll just write it down. And this goes to 0. Now here it is very similar. This goes to 0. Now this is varying, but it is bounded by 1 or something, because xn were just results of rotating x, or u, which was a fixed vector, and these are orthogonal transformations, so it's length of u at most. So this goes to 0. And to finish this bubble, if you are looking at this pi an x and yn, what is that? Well, you remember this is xn was k n u, and this guy is r n v, and you can move this around, and you have that. And although I tried, it didn't quite match, but anyway. Okay. So we made our first step, reduction to a situation where an's shrink. Second thing, I have.
25 more minutes.
Oh, thank you.
You also speak 60 minutes, right?
Yeah. That's Israeli 60 minutes. So, the next thing is known as Mautner's lemma. It is a really, really clever thing, but very simple. And people use infinitely many versions of that. So, where am I? It goes like this. Suppose that you have a representation of some group. This is some group. Into the unitary of some Hilbert space. Assume that in G you have a sequence AN of some elements and another element H, and they satisfy that AN inverse H AN, so that if you conjugate H by AN, you shrink to the identity, converges to the identity. So the ANs that, so you should think of ANs as in like SL2R. My ANs are going to be something like this. And my element H is going to be something like that. And yesterday, Manfred wrote the crucial relation satisfied by those. Well, I can put here 1 OS. So this is going to be an element of this subgroup. This conjugation actually gives you, if you do the calculation, a similar element but much shorter s, e to the minus 2tns. I think it's just easy calculation, and this goes to identity as tn goes to infinity. So you should keep that as an example, but this is general theorem. It doesn't have to do anything with anything. And now, what is the theorem? And suppose that you have vectors x and z in your Hilbert space, and they satisfy that pi an of x converges to z weakly. Now, weakly means that inner product with any other vector will give you that the dot product with another vector y of this converges to the dot product with z. So there's this weak convergence. So suppose that this converges weakly, then z is fixed by h. Okay, that's the thing. What's the proof? Well, let's look at the norm of pi h a n x minus pi a n x. Now, an are unitary vectors. Pi an, I mean, pi an are unitary operators. They don't change norm. So this is whatever it is. Let me apply pi an inverse to this thing. It won't change the norm. So this is going to be equal to pi an inverse pi h an x minus x. Right? I haven't done anything wrong. Now, this is phi an inverse hn, x minus x. And the thing is that this goes to 0, because my representations are continuous in strong topology, remember? We have a sequence going to identity, then, this holds. Then every vector by this sequence gets more or less to itself. Okay? So what we have is that pi h, Okay, so we have that. But notice that we assumed, just on the left here, that pi a n x converges to z weakly. If I apply pi h to this, I will have weak convergence to pi h of z. But at the same time, I got a strong convergence of that, even in norm, by the above calculation. So the same sequence of vectors converges weakly to something and strongly, which implies also weakly, to another thing. This was...
This is not x to pi a n.
Yeah, pi a n. Pi a n x, which itself, so no, sorry, the difference between them, okay, luckily I don't have much room here to try to
The difference converges
it does
to zero.
converge to z, because this guy converges to z weakly, and there is a body of it which is at shrinking distance from it. It has to converge also with the usage. So both of these convergences are weakly. So there was a sequence of, I think of it this way, un converges to v weakly. And there is another sequence wn, and what you know is that the distance between un and vn shrinks. Claim that this implies that wn also converges to v weakly. What do I need to do? I need to check the inner product of wn against arbitrary, I ran out of letters, p, lambda. I need to check whether this converges to z lambda. Well, you compare that with this definitely converges to z lambda. And the difference between those shrinks to 0. These are convergences of regular, numbers. So we had this. This is given. This follows, and this follows from that calculation, and this other assumption. So the result is pi h of z equals z, and this is Mautner's lemma. Now comes step 3, which is known as, I think, Gelfand's trick. I don't know why. So, step 3, case of G equals SL2R. Okay, let's just focus on a special case because we'll need it anyway. Every semi-simple Lie group is built out of SL2Rs put together in some fashion. So we have, so assume, we had the interrepresentation of this G on some Hilbert space. We assume it does not mix as it should. So it has a pair of vectors uv in the Hilbert space and some sequence Gn going to infinity, such that matrix coefficients for that representation of SL2 along Gn not going to 0. Then you do step 1 again, and no, we just did them, and you get that by step 1 you get vectors x, y in the Hilbert space, and now a sequence of diagonal entries. Now Tn goes to infinity such that f x, y of An remain also bounded from 0. Okay. So how did it go? We wrote Gn in k decomposition, and these were the diagonal entries that entered there. They were in A+, which is where the Tn's are positive. Now Gn's went to infinity. You cannot make long matrices by writing something in k times something in A, something in k, unless you use longer and longer parts of A. Because if that were bounded, then the whole thing would be bounded, and that's not the assumption. So Tn's go to infinity. I just explained that. Okay. Now we use Mautner's lemma. There is a calculation on the right that we prepared. If you take these entries, these matrices, then An shrinks them. So how do I jump into Mautner's lemma? I need some z. So okay, so I'm going like this. So look at pi An x. This is some sequence in the Hilbert space. Now this sequence is, let's say x was a unit vector or a vector bounded by 7. Then this sequence consists of vectors bounded by 7. Yeah? So they're in a ball of radius 7. Now, bounded balls are compact in weak topology on the Hilbert space. Balls are compact, or pre-compact. Closed balls are compact in weak topology. So, without loss of generality passing to a subsequence, I may assume that pi An x converges weakly to some z in the Hilbert space. Okay, this is very cheap. Compactness is cheap. But usually, if you take vectors in the Hilbert space, they converge weakly to the 0 vector. They just keep changing direction, and that way they converge. But, crucial key observation is that z is not 0, because pi An x against y converges as numbers to z against y. This is the this is what weak convergence is about. But these things are bounded away from 0. And therefore, this is by absolute value greater or equal than A1, which is epsilon 1, which is positive. And from this you get that z, that this dot product is not 0. And therefore z is not a 0 vector. That's the crucial thing. You work very hard just for that little thing. But now, and we have Mautner's lemma proved here. Let's erase. Now by step 2, what do we know? Z is fixed. Z belongs to the Hilbert space, Hilbert subspace of vectors fixed by the group H. H is going to be this whole group of all of those guys. Okay? This is what we've got. And this is a non-zero vector. Okay, now look at the matrix coefficient with respect to z. So look at the function f from G to complex numbers, which is the fzz. In other words, f of G is inner product pi G z against z. Okay? What do we have? Well, one thing is that f of gh equals f of g for every h in this of that form. Because z is fixed by h. You have pi, because this is pi gh zz, and this is pi g pi h z z, and this is pi g zz, right? Okay, and this is that. Also, can I erase? This is 1. 2. This function, so this function is invariant for its function on G, on SO2, but this variant on the H acting on the right. It's also invariant on the H acting on the left. Why? Same thing, but you have pi H on the other side, because pi H is unitary. You can move it to the other side, right? This is pi h pi g z z. Well, but this is pi g z, and here pi h conjugate. But this is the same as pi h inverse, and this is still in h, so it is still z. So we have this pi invariance of function. Let me go here. And here is this beautiful thing that I refer to as Johann strip. And it goes like this. For some water. You think of by 1, using this identity 1, f descends, let me try this, that's the order, okay. F descends to a function g mod h to complex numbers, right? Because it is on posets, right? Now, what is g mod h? G is SL2R. SL2R, its purpose in life is to act by linear transformation on R2. It acts on R2 transitively, well, if you remove 0. Right? On R2 without 0, it acts transitively. And its stabilizer of, so it is G mod stabilizer of a point, but if you take the first unit vector, its stabilizer is exactly h. So G mod h is R2 without the origin. So my function descends to a function on R2 without the origin. Now I should have pointed out that because our representations are continuous, the matrix coefficients are all continuous functions. I should have said that. So this was a continuous function on G, and it descends to a continuous function on R2 without the origin. So here is R2 without the origin. I draw it like this because I want to remember that f by 2, this function, the new function f1 is a constant on the h orbits acting on G mod h, because it is invariant also under the left h action. Now H acts on G mod H. Well, you know in group theoretic terms, but you also know in this description, because what an element 1s01 does to the vector xy is what I'm about to write. X plus sy, y. So that abstract action is actually realized by the usual linear action on R2. And the orbits as n runs, the orbits of this H action are the horizontal lines, all except the x-axis. On the x-axis, these are all fixed points, because this corresponds to y equals 0, so they're all fixed. And there is consistency, because this action is very fast if you go away from the horizon. If y is big or very negative, then it goes to the opposite. And it slows down as you approach it. But f1 is a continuous function which is constant on h orbit, so it's constant on each one of those horizontal lines. Because of this, f1 is constant. Observe that f1 is constant on this as well. On, how does it go? x0, x not equal to 0. On this thing. Why? Because if there were 2 points that you claim the function has different values at, okay, this point and that point, I can get a horizontal line very close to them so that the function is not differ much here and there, and here and there. But the values on this thing are going to be the same. Okay, so it is a deep calculus observation. But we get that this function is constant on the horizontal line. Now, you get, as a conclusion, that f1 at any x0 is equal to f1 at 1, 0. Now, who is 1, 0? This is exactly f zz of the identity. And this is precisely the dot product of pi identity z with z. This is the length of z squared. This is going to be true for every x. In particular, if I write here e to the t, this is also going to be true. Okay, so for every t in R, I have that. Now, what is written here is fzz of the element e to the t over 2, e to the minus t over 2. Because this element, what it does, so the action, so we consider the action of H, the upper, these matrices on G mod H. If you look at the action of A, the diagonal subgroup on G mod H, or on R2, it's the action by homotheties. And in particular, here is the point 1, 0. If I act by homotheties horizontally, it takes me to places like this. Okay. So what we've got is that this is equal to that. Call this element AT, alpha t. This is pi AT ZZ. Okay. Now, by Cauchy-Schwarz inequality, if this is equal to that, this implies that pi ATZ equals Z. So we started from a vector, which was almost, we did some work, but we looked at these matrix coefficients, used topology of G all the time. So these were continuous functions. We used diagonal elements in Mautner's lemma to show that to find a vector which is invariant under such elements, and then use this Gelfand trick that the same vector is automatically also invariant under the diagonal element. And now, I'll just take 30 seconds to finish this case. What you do is you say, okay, then Mautner's lemma again. You see that this Z is also fixed by these matrices. Why? Because Z was fixed under those, H plus. It's going to be fixed under H minus because by Gelfand's trick we showed that it is invariant under or fixed by the whole diagonal subgroup, whether positive t's or negative t's. Right? We had some sequence at the beginning. From that we extracted things, worked. Now we got conclusion that the whole diagonal group fixes it. But in the diagonal group you can go forward and you can go backwards. If you go backwards, then the directions that you shrink by commutation relation that we have erased by now is not the upper four-cyclic thing, but this lower. And by Mautner's lemma, the same vector is going to be now fixed by this lower thing. Now, these two types of matrices generate the whole group SL2R. So Z is fixed by all of SL2R, and H pi G is not 0. So we started with the, contrapositive proof, whatever, that the matrix coefficients were not vanishing at infinity. The conclusion was that there were non-trivial invariant vectors because we found this Z, which is invariant under all 5. Now I didn't do the full SLDR case. It is like 5 minutes away, but we'll stop here. Thanks.
Sorry, questions, Felix?
Could you explain again why G mod H is the plane without origin?
Because G acts, so SL2R acts on R2 without origin. It acts transitively. Any non-zero vector is part of some basis. You can take it to the standard basis by, any vector, you can find another vector so that the pair will determine a parallelogram positively oriented of area 1. Then you can find an element of SL2R which brings this to the standard square. I mean, there is a linear transformation, but it will have determinant 1 because of the assumption that I made. So SL2R acts transitively on R2 without the origin. So take some point. Well, of course you take the best point. We say it's just general vector space, but we all secretly know which points are good. Yeah.
H is a stabilizer of
yeah.
So
I mean, you defined H before, but it turns out that it's the same thing as the stabilizer.
Yeah. Thanks. So in the next talk, I'll try to do a very rapid introduction to entropy.
I think we can thank Alex again.